Hi, in this video we want to talk about trigonometric equations. Now these are different from the expressions we just talked about, and with trigonometric equations they are also known as general solutions, and we want to take a look at why that is the case and just a short example on that. So what I have here drawn is a function y is equals to sine x. And again, I've repeated the function over and over up until like somewhere 1080 degrees. And this is just for explanation purposes, but you should also get used to the idea of trig functions being this repetitive. But what we want to solve for today is we want to solve for x. So you know how we usually do that for functions, like we can have a parabola like this, and then we can ask for which value of x will the y be equal to 0. So if the y is equal to 0, that means we're looking for the x-intercepts, right? So that means we take whatever we have, the ax squared, let's just call it 2x squared minus 3x minus 2 is equal to 0. This isn't this function here. If you were to draw it out, it's just an example that shows that we're trying to find x when our y is equal to 0, right? And y is described by this function. So in this case, we're trying to find our x when our y is equal to a half, basically when sine x is equal to a half. So how do we go about doing this? Well, here we could actually draw the x-axis. We can see the points where our function is 0. Here we want to see the point where our function is a half, which could be somewhere over here. So drawing that, we can already see something is amiss here, like something is weird, because it doesn't only intersect it not once, not twice, but repeatedly. If I were to draw this function going on and on, there would be indefinite points in which they would intersect, right? It intersects there and there. Our function is half over here, it's half here, it's also half here and half there, it's also half here and half there, half here and half there. As we can see, it goes on and on, half here, half there. But we can see that we know intuitively that our function is only unique from 0 to 360. Therefore, if anything happens in this region, it's gonna repeat after 360 degrees, which means between this point and this point there are 360 degrees. Between this point and that point there are 360 degrees out of phase, basically. So with that knowledge and that understanding, we can kind of understand why they call it a general solution, because it's not a specific solution. What we end up with is just an equation that tells us how unique the solution is, like from which point do they start repeating. So if we were to solve this trig equation, we'll take x or sine to the other side, and what we get there is not our answer for x, but rather the reference angle. So the reference angle will be equal to arc sine of a half, and we know that arc sine of a half, or sine 30, is equal to a half. Therefore the reference angle has to be 30 degrees. Then from this point on, here's what we do. In order to get this 30 degrees, I did not consider the sign of my function or of my value here. I just took it as it is. So if it was negative, I still would have just considered the half to say, okay, which value gives me a half, not which value gives me a negative a half. So I only look at the value, not the sign. Once I have my reference angle, then I ask myself, okay, when is sine positive? As we discussed in the previous video, sine is positive in the first quadrant and in the second quadrant. The answer for the first quadrant would be that x is equal to 30 degrees plus 360 degrees k, where k is an element of all integers. So what does this statement say? It's saying that here it's 30 degrees over here, but this is going to repeat after every 360 degrees. So the next point is going to be here at 390. That's when it's going to happen again. That's when we're going to get the other half. But this doesn't give us our entire solution. That's why we had to write down that 30 is only the reference angle. There's also another one that happens over here within this region, or respective to 180. And we know that in the second quadrant, sine is also positive, and in the second quadrant we have 180 minus 30. So we say 180 minus our reference angle plus 360k, where k is an element of 4 integers again. 180 minus 30 is just 150, so we write that as it is, plus 360k, where k is an element of all integers. Then this is it. These are your solutions. So this would be the second solution over here at 150. And again, this repeats after every 360 degrees. So the next one is going to be 360 plus 150, which if you add it up would be 510. So that would be at that point over here. And that's about it. So that's how you work with trig equations. You also get specific ones that are kind of weird. You could get something like sine x minus 30 is equal to sine of 30. In this case, or let's say 15 or something. In this case, you can just equate, because you know how you use that law to say that 2 to the power of x is equals to 8, but I'll solve this as 2 to the power of x, rewrite the 8 in terms of 2, and say that this is equals to 2 to the power of 3, then the bases fall away, but they're not actually falling away. Since this is an equal sign, we know that whatever's on the right hand side should be equal to whatever's on the left hand side. So if we have 2 to the power of something on this side and we have 2 to the power of 3 on this side, it means that something, which is x, should be 3. It's that simple. So over here as well, we can do the same thing. We can say x minus 30 is equal to 15. And then you can do that for the first quadrant and also do that for the fourth quadrant, or not the fourth, but the second quadrant, where sine is also positive. And then you can work with it that way. So this is how you solve trig equations. Don't consider the sign when considering the reference angle. Only consider the sign in the event of you trying to figure out the quadrants to use. So as another example, as a counter example, imagine if it was minus a half. Therefore my reference angle will still be 30. But now I'm no longer looking at the first and the second quadrant. I'm now looking at the third and the fourth quadrant, because this is where sine is negative. All of them are positive here. Sine is positive there. Only tan is positive here. Only cos is positive here, which means that I don't consider those, but these quadrants. So my answer would have been something more like the third quadrant, 180 plus 30, which would give me 210. And then my other one would be in the fourth quadrant, which would be 360 minus 30, which would be 330. And every time we put plus 360k to show that this answer is going to repeat at the set period of our function. Then the last thing to mention would be, if you were to have something like this, sine 2x is equal to minus a half, basically, or a half. Let's just take it like that. The reference angle is still 30 degrees, but now instead of writing x is equal to 30, we say 2x is equals to 30 plus 360k, and then we first simplify this. So this will be the first quadrant answer. We divide everything by 2 to get x is equals to 15 degrees plus 180k. And then we can do the same thing for the second quadrant answer. Would say 2x is equals to 180 minus 30 plus 360k. It's important that the 360k is included in the operations. Therefore, we can divide everything by 2. 180 minus 30, that gives us 150. Divide that by 2. So you have x is equals to 150 over 2 plus 180k as your answer. So those are the kind of like three different situations that you can get that you need to be able to work with for trigonometric equations.